Let's get started. By a show of hands, how many of you can hear me? Okay, okay. All right. Thank you for letting me know. Let's get started. This is what we started doing in the last class. Okay. As a matter of fact, if you think about it, we covered all the big topics that we want to cover for the single transistor amplifiers. Let me quickly, in a very deliberate manner, review what we did in the last class. Okay, this time we are going to go from top to bottom, from beginning to end. Okay, amplifiers are usually modeled using two ports. There is an input side, okay, and there's an output side. Okay, there's an input side and an output side. The input can be current or voltage. Okay, the subscript I shows that is input. The output can be, okay, the output can be current or voltage. Okay, so the subscript O represents that it is output, while the subscript I means it is input. Depending on what we have, the different combinations of input and output, okay, we can have an input current and an output voltage, okay, or any other combination between the four input and output variables. Okay, if we have an input voltage and an output voltage, we have a voltage amplifier, so on and so forth. Okay, based on the combination of input and output variables that we chose, we can have four different kinds of amplifiers. Okay, so here is the typical amplifier model, and you want to make sure that you're not losing a whole lot of your signal to the amplifier resistances. The ones shown in charcoal black, highlighted in black, RS, okay, RS, and RO, are not. These are of importance to us. Okay, so the amuse me is a little theory a little bit here. Take a look at the current that is flowing here. Okay, the current that is of interest to me, I. Okay, this is what has been amplified actually. Okay, this is the current. I want all of that current to be flowing to my output. Okay, I want a whole lot of current being delivered to the output resistance RL, because that's my load. I want most of the voltage drop to appear across load resistance. The maximum current should be delivered to that. Okay, in order for that to happen, because this R naught is in parallel to RL, okay, I want this parallel branch R naught to be really, really large, ideally infinity. If the parallel resistance is infinity, R naught is infinity, or really large, okay, then most of the current is going to flow through the load resistance, and then I'm losing very little in the way of commissions. Okay, thinking in terms of the analogy of financial investment. Similarly, so parallel resistance, if it is in the output, you want it to be ideally infinity. How about the resistance in series, something in series? If I have any resistance in series, okay, then I want that series resistance to be as small as possible. That way, That way, the voltage dropped across that series resistance is small. Okay, I want most of the input that I apply to show up across this resistance Ri. Okay, so any resistance in series should ideally be R series. It could be R out as well. I want it to be close to 0. So resistances in series, the external resistance, not the external resistance, but the source and load resistances in series, the source and output resistances, okay, the device resistances in series, well, they should be close to 0, while the parallel resistances should ideally be infinity or a really large value.
I have a question, Professor.
Yes.
Why do we model the output resistance for a current parallel and for the voltage in series? Because if we model the output resistance for current in series, then we won't lose any signal.
We will, in terms of, see, the idea is when we are passing a current through any resistance. So this idea is the Norton's equivalent, right? A current source with a parallel resistance is the Norton's equivalent. So that provides, okay, that provides a voltage here, okay? So if you think about it, okay, if there is a constant current source, okay, if there's a constant current source and across its terminals, okay, across its terminals, the voltage is going to be the same across all the parallel paths, okay? So this idea of current source in parallel with the resistance is the definition of Norton equivalent. Similarly, a voltage source, okay, a voltage source with a series resistance, well, that's the definition of a Thevenin's equivalent, okay, of a Thevenin's equivalent. When you're looking at the open circuit voltage here, it has a set, okay, it has a set voltage that you'll see across these two terminals, okay. So this is the standard form of representing voltage and current sources, okay. The resistance of the voltage source, okay, is in series. The resistance of a current source is in parallel, okay. Now the idea is, even with a current source, okay, even if I were to have a constant current source, okay, a constant current source, I source, with some resistance R source, okay, and then there is RL. We can't get away from the fact that there is going to be some voltage source, okay? So IS, maybe the current flowing through both of these terminals may be constant. Sure, I'll give you that. But think about the voltage, okay? There is going to be some voltage drop here. There's going to be some voltage drop over there, okay? If this resistance is large, then most of the voltage is going to drop across this resistance. And if this resistance is relatively large, most of the voltage is going to drop across that resistance. So we cannot run away from the fact that even if I have a current source in series with a resistance, that is not going to give me a no signal loss condition. That was your question, right? If I had a current source with a series resistance, then the idea was that we may not have a signal loss. Well, that's not the case. As a matter of fact, even with a current source in series with a resistance, we do have a signal loss, okay? But the Norton's equivalent, one way to abstract away the operation of a black box is to think of it as a current source, with the equivalent resistance. Okay.
Thank you.
Okay. So there is going to be some signal loss for any parallel output resistance. We want it to typically have a value, ideally infinity. Okay. I want it to have a really large value. And then I want this guy, any series output resistance, to have a very, very small value. Okay. So that's the idea that we want to get. Okay. So this, we looked at how there is a voltage division here on the input side, and then there's also a voltage division on the output side. Okay. This R naught by R naught plus RL is the voltage division. Okay. The current division between the two. Okay. R naught by R naught plus RL is the ratio of current, is the fraction of current that flows to RL. Okay. So this is my generic idea of modeling amplifiers using two-port networks. Okay. And then we looked at the 4 different types of amplifiers possible. Okay. 4 different types of amplifiers possible. V output has a resistance in series. So I want the output resistance to be 0. Similarly, um, the I output has a resistance in parallel. Therefore, I want anything in parallel, I want it to be infinity. So the general characteristics that we looked at earlier, they apply here very well. Okay, depending on what the input terminal is, input signal is, and the output signal is. If the input is a voltage, output is a voltage, I have a voltage amplifier. If the input is a current, output is a current, I have a current amplifier. Transconductance, trans resistance amplifier. We looked at this in the last class. And then in order to minimize the signal loss, okay, there are different conditions. So you want to understand that anything in series should ideally be 0, anything in parallel should ideally be infinity. Okay, when it comes to the output side. Okay, when it comes to the output side. Then we looked at single transistor bipolar junction transistor amplifiers. Okay, and the idea I mentioned was, as long as I do not show any of the inputs here, okay, remember I tactfully erased all the inputs. So all of these look exactly the same. They are exactly the same when there is no input and output applied. But when there is input and output applied, depending on where I apply the input, where I apply the output, I can have 3 different configurations. Okay, if I don't apply the inputs at all, then all of them appear the same. Okay, all of these appear the same. But once I begin to apply the inputs, okay, then they appear differently. If they behave differently. Okay, so if I were to apply the input on the base and the output on the collector, well, then it is the common emitter, so on and so forth. If the input is on the emitter and the output is on the collector, then I have the common base amplifier, so on and so forth. Okay, and then input on the base, output on the emitter. This is also called emitter follower, remember? The output is simply going to follow the input. So if you were to do that, if you were to do the V output versus V input graph, it's probably going to look something like this. Up until 0.7 volts, and the output voltage is below 0.7 volts, 0.7 volts below that guy. It's not going to be any difference, but it's going to be offset by 0.7 volts. Okay, so that represents the forward bias voltage of a MOSFET, of a BJT. Okay, so that's this guy, 0.7. voltage between base and emitter. Okay? Now, the type of the amplifier is completely determined by where the input is applied and where the output is measured. Okay, that determines the kind of amplifier that we have here. Okay, so the first thing we did was to look at the resistance. Okay, let's see. The first thing we did was, let me do that. This guy, okay, was to get rid of all the inputs. Okay, get rid of all the inputs and see that they're all exactly the same. Okay, they're all exactly the same. There is a resistance in the emitter, there's a resistance in the collector, there's a resistance in the base. Okay, okay, when I'm not applying any input at all whatsoever. Okay, then I know for a fact that they're all identical. Okay, I'm not applying any input whatsoever. Then they're all identical. There is just one transistor with 3 resistances in each of the in the terminals. Okay, now what I'm interested in finding out is the resistance looking into each of these. What is the resistance looking into the base? Okay, our input looking into the base. What is the resistance looking into the emitter? What is the resistance looking into the collector? Okay, and they're going to be the same everywhere for all 3 topologies. So if I calculate one set of RIE, RIC, and RIP, it's going to be the same across the board. Okay, they're not going to change based on where you apply the input or the output. So the values of these guys, okay, are input looking into the base, okay, are output at the collector, or output at the emitter. These are not going to change based on the input and output configuration. That's the observation that we made earlier. Okay, so for single BJT amplifiers, what I want to find out is expression for RIB, RIC, and RIE. Okay, if I find these out, then I should apply, I should be able to use them over and over again for any of the 3 different configurations of amplifiers. Okay, so in the last class, I mentioned that we want to apply a test voltage, test current method, and I'll show that to you how to apply that in just 1 second. But then let's recap the different values here. The intuitive idea behind RIP. When you're looking into the base, you will find R pi, and you will also see that the resistance in the emitter is reflected back into the base. It's almost as if if you're looking into the base, you're looking at R pi plus a big value times RE. Okay, looking into the base, this is what you would find. Okay, and that is a simplified idea of what you'll see in R base. Okay, R base is R pi plus the reflected reflected up value of RE. Let's see, looking into RIC. Looking into RIC, okay, this guy, you will find R naught, okay, that is simply multiplied by this guy, okay. So R naught, that is magnified, that is multiplied to a large value by this guy. Okay, looking into RIC. So we still did not look at the case where I'm using an external resistance RC. Remember DC, there is no RC over here. Okay, we're going to take that into account later on. All that we need to do is to include RC in parallel. Okay, so similarly, I have not taken into account the RB over here. RB. So if I want to take that into account, I do this in parallel with RB. Okay, so there is certain things that I did not still take into account, but it's easy to take them into account at a later time. Okay. Okay, so that's looking into the collector shown in blue, looking into the base shown in green. Okay, let's calculating the resistance looking into the emitter is a bit more interesting problem where we have to use not the hybrid pi model, but a T model. So what you'll see is simply that when you're looking into the emitter, okay, when you're looking into the emitter, let me use this color over here. When you're looking into the emitter, what you will find is RB plus R pi, okay, RB plus R pi, okay, RB plus R pi, okay, RB plus R pi, that is scaled down. Remember, earlier I had R pi plus RB, that is RE, that is scaled up. Remember, RE was scaled up earlier. We go back, RE was scaled up to a large number, okay, reflected up. But here, when you're looking into the emitter, that's a different idea. What happens is R pi plus RB, that is scaled down by the same factor, beta plus 1. Earlier, I had R pi plus RE that is scaled up to beta plus 1. Then there is 1 plus RC by R naught. Okay. Then there is a voltage division between RC and R naught. Okay. You're looking into the emitter. So you're looking into the emitter right here. What you'll see is that there is some R pi. Okay, there's a relationship between an R pi and RB, which are exactly the same. Okay, so R pi plus RB by beta plus 1, exactly the same in the sense they're very closely related. If you know R pi, you should be able to calculate RE. If you know RE, you should be able to calculate R pi. Okay, so R pi plus RB by beta plus 1. Okay, so that's the idea of emitter. And we'll come back. I'll come back to show you how to calculate these values, okay, these terms. Now, if you're looking into the emitter, you can approximate under certain conditions when the RC is very large to be this to be equals to R pi plus RB. But that's an approximation that you may not be using too often in the class, okay? But it's good if you know the limits. Okay, resistance looking into the emitter. Okay, here is the shortcut approach. All you need to know, here is the slide that you want to tattoo on this on your hand if you want to. Okay, so the idea is this: you want to know the expressions for current IC and IE. Okay, so because you want to know the small signal currents IC. Okay, the small signal current IC. Okay, you want to know the small signal current IC, IE, okay, and of course IB. So you have the expressions for those. IC is beta times IB, IE is beta plus 1 times IB. Then you need to know the resistance looking into the base. Okay, resistance looking into the base is R pi plus beta plus 1 times RE. Okay, similarly, you want to know this guy, okay, R collector. Looking into the collector, you have R naught that is multiplied by a large number because of degeneration. Okay, this is the concept that we just looked at. Looking into the emitter, the resistance RE is R pi plus RB by beta plus 1, that's a scaled down version of it, and the 1 plus RC by R naught, which tends to beta plus 1 times R naught. Looking into the emitter, it tends to be a large number, R beta plus 1 times R naught. Okay, now all we need to do is this, to solve most BJT circuits. The currents flowing in the base emitter and the collector. What are the currents flowing? I'm talking about the small signal currents IB, IC, and IE. Okay, so in order to do the AC or the small signal analysis, you should have already done the DC or the large signal analysis. And these parameters, the small signal parameters, are important to us in reference to the operating point or the quiescent point. Okay, and then the resistance is looking into the base. Okay, so once we have these two terms, it's simply a matter of applying the Ohm's law. If you want to find out V out, all you have to do is the I out, and I'll show you an example. Okay, okay, where did that go? Okay, okay. Now, if you have IB, IC, and IE, the values for that. Okay, and if you have R, IE, R, IB, R, IC. Okay, in order to find out the gain, you have to, it doesn't matter where you apply the input and output. Let's say you apply the input on the base. Okay, input is on the base. Okay, that's your input. Okay, input, and your output is this guy, collector. Okay, let's say that guy is your output. Okay, all you have to do is V out. If you're interested in calculating V out over V in, or the voltage gain of a common emitter amplifier, well, all you have to do is to multiply I out, which is IC, times RIC, okay, over I in times RI base, right? Because what is the voltage across the output? That's Ohm's law. What's the voltage across the input? So the idea of going through this hassle of finding out the expressions for RIE, RIB, and RIC is so that our overall calculation of the gain is very straightforward. That's what I'm interested in doing. Okay, so even though it's a little tedious, it's not um, incredibly intellectually challenging, or a leap of intellectual concept, so much as it is brute force manipulation, algebraic manipulation. Okay, once we calculate this RIC, once we know these terms, okay, once we know these terms, okay, calculating the gain is simply a matter of applying Ohm's law. Okay, so it appears like magic, but it really is not, because if we already have a an easy way to calculate these terms, okay, calculating gain is straightforward. This does not work for feedback circuits. When I incorporate explicit feedback, this does not work. Okay, let's see. Common emitter amplifier. Let's see if we can use the idea that we discussed so far. Okay, so the common emitter amplifier input is on the base, the output is on the collector. Okay, so this guy is input. and this guy is output. Okay, now how do you find the gain? Okay, notice that the output here, R output, is the resistance looking into the RIC in parallel with external resistance RC. So far, we have not taken RC into account. Okay, so let's see. To find the voltage gain, all we have to do is to calculate V output, which is the resistance in the output times IC. Remember, there are three terms that I need: IC, RC. Okay, RIC parallel with R external resistance RC. So the resistance is external resistance times external resistance times a current. That's all I'm using to calculate voltage, output voltage. Okay, that's the output voltage over, okay, that, and the input voltage VI. Okay, the input voltage is simply IB times RB plus RI. Okay, RB plus, this is the RB, R pi plus this guy is RAB. That's this guy. This is RB. So all I'm doing here is to calculate the current flowing in. Let's do that calculation here. Now, this is minus beta IB R naught is V output, right? Because this guy minus beta IB is IC. Okay, so all I'm doing is the current flowing in this resistance, okay, or the current flowing into the collector IC, and then there is a resistance RIC looking into the collector. Okay, so R output is going to be the parallel combination of RC, and this is our RIC. Remember, what is this term? We know that RIC, resistance looking into the collector, RIC, that is going to appear in parallel with RC. That's all there is to it. Okay. At the output node, the R output is going to see one parallel path, RIC, down into the collector, and one path up into the power supply. That's their parallel. So output resistance times the output current, okay, will give you the output voltage. Output current IC times output resistance R naught will give you the output voltage. Similarly, the input resistance, so all of that is the input resistance. So input resistance times the input current will give you the, so there's an IB in the numerator, there's an IB in the denominator. Input resistance times the input current gives you the input voltage. So in order to calculate AV, all I have done is to look at the R output times I output by R input times I input. I input is IB, R input is RB plus RIB, right? RIB plus RB. Similarly, R output is RC in parallel with RIC, and what the heck, crappy. Okay, should be more careful in writing this. Okay, so gain is really V output over V input, which is R output times I output by R input times I input. Okay, I output is IC, R output, IC is the same as beta IB. right? So R output is RC in parallel with RIC. If you're going to look at the resistance R0, looking in, you would find one RIC over here, one RC over there. That's the idea of, so the bottom line I'm trying to mention is that if you know RIC, RIB, RIE, the internal resistances, looking into the base, looking into the emitter, looking into the collector, okay? Then you can calculate R output and then multiply that by I output, okay? So calculating the gain is simple matter of V output over I output. V output over V input, that's the gain, okay? So here is, yes.
When we, yeah, I have a question. When we calculate R out in the formula, we take into account RC, which is the external resistance in the collector node. But when we calculate RI or RN, we don't take into account RB in the formula.
We do take into account RB. So take a look at this. There's this RB, right?
Yes.
RB.
So in the formula down below the figure, we don't see any RB.
Okay, yeah. Thank you. Okay. Yes. So all of this is R looking into the base. Okay. RIB plus RB will give you RI. That's a good question. That's a good point. Thank you for pointing that out. Okay. So there is this plus RB because this RB is in series with, so let me write it here, RB in series with RIB. IB is that guy, RB is this guy. The sum of these two will give me RI, looking into the base through this guy. Okay. Other questions, please. Okay, now the PowerPoint actually does not, it should really have mentioned that this is RIB. If this is RIB, then I don't have to add RIB over here. I can simply add RIB plus, so this is RIB. So all of that is RIB plus RB. Okay, so there are two ways to express the same thing. I can call this as RN plus R base. Okay, other questions, please. So I want to call this as RIB. That way it is in alignment with what we have discussed so far. Okay, let's call this as RIB. RIB. Okay, other questions, please. Okay, so if you think about it, when you go back, so there is this RIB looking into the base. Okay, RIB looking into the base. RIC looking down into the collector. We only looked down, but if we look up, there's an RC, so we have to account for that as well. That's where the parallel comes in. Okay, that's where the parallel comes in. Okay, that's where this parallel comes in. Okay, so that's the idea. We can also define what is called a transconductance, which is nothing but input voltage in the denominator, output current in the numerator. Okay, and we can define that to be negative GM by 1 plus GM RE. And then This is the transconductance. Other questions? Okay, common emitter amplifier. Let's look at the common base amplifier as well. Okay, for the common base amplifier, if you want to calculate the gain, AV, all you have to do is you have to calculate V output, okay? V output, which is R output into I output. You calculate V input as R input into I input. Okay, input is on the emitter. Okay, therefore I input is this guy. Okay, and then V input therefore is going to be I input times this guy, IE times this guy. Similarly, V output is going to be I output, which is IC times R output, which is R naught, that is V output. Okay, so this guy gives you the relationship between V input, I input, and R input. So R input, I input, and V input is shown in the purple function here. Okay, once you manipulate this, what you will see is V output over V input. Okay, V output over V input is simply beta R naught by RB plus R pi plus beta plus 1 times RE. Okay, so typically what happens is this will approximate to RC over RE, or the voltage dropped across RC over the voltage dropped across RE. Okay, so that's the gain of the common base amplifier. Let's look at the common emitter amplifier as well. Let's look at the common emitter amplifier, common collector amplifier gain as well, or the source follower. Okay, even in this case, the gain is V output over V input, and the exact same thing applies. Okay, copy that. I am going to simply duplicate it here. Okay, the V output is R output times I output. Where is the output now? The output is on the emitter. Okay, the output is on the emitter. So I better change these colors here. So this is purple. Okay, that's the output. Okay, this is blue in this case, which is the input. Okay, let's see if I can do that. Okay, this is the input. Okay, the input shown in blue. If you look at the schematic, input is on blue. Okay, on the base, the output is purple, shown on the emitter. Okay, so what is R output? R output is nothing but RE in parallel with RIE. So this guy is RIE. This guy is RE. Okay, so you can approximate all of this guy into a small value. Okay, into a smaller term. Okay, so this is your R output because the output is on the emitter. Look at where the input is. Input is on the base. So the R input is RIB. So this guy is RIB plus RB. Remember when the input was on the base, okay, there was RIB, there was RB. This is exactly what we did earlier. Go back. Let's go back to common emitter. When on the common emitter, look what I have here. Okay, there is this RB in parallel in series with RIB. Okay, when the input is on the base, the input voltage is going to be the exact same thing, RB plus RIB plus beta plus 1 times RE, all of that multiplied by IB. Let's take a look, okay, in the common collector amplifier. Well, the denominator is exactly the same. That's because the input is still on the base. RB plus R pi plus beta plus 1 times RE times IB. Okay, where did that IB go? Well, there is this IB here, but remember, there was supposed to be an IE here, but that IE has been written as R beta plus 1 times RE times IB. So when they cancel out, okay, left with the voltage on the output is the output resistance times the output current divided by the input resistance times the input current. Simply Ohm's law. Questions, please. Questions so far. So what you want to recognize is, like I mentioned in the last class, okay, I mentioned in the last class that this denominator is very, very close to the numerator, okay? The numerator is exactly, not exactly, but very, very close and smaller than the denominator. So this value is always going to be positive and very close to 1, but less than 1. Questions, please. Okay, all of this, we actually talked about this in the last class itself. The only thing that I'm mentioning freshly in this class is the idea of using the 3 terms, the output currents, IB, IC, and IE, and the output voltages, RE, RB, and RC. Okay, if I know how to use them in conjunction with the currents, then calculating the gain or the transconductance is straightforward. Okay, so that's the idea of BJT amplifiers. Let's quickly see if I can go back, okay, and find out. I'll give you an example, one example of how the resistance has been calculated looking into the base. Okay, so far all I did was to mention that the RIB value is R pi plus beta plus 1 times RE, right? Well, how did I arrive at that? So it's a matter of applying KCL and KVL at different nodes. And hopefully I want to give you an example, one example on how we did that so that you can apply the same to others as well. Okay, let's see. The general procedure to find any resistance is, let's say you're trying to find RB. Okay, when you're trying to find RB, the first thing you want to do is to kill all independent sources. Deactivate independent sources. By deactivating, I mean voltage sources should be short circuited. Okay, the current sources should be open circuited. Okay, if there is any independent voltage or current source, the first thing you want to do is to deactivate them. Okay, and then you apply a test voltage and look at the test current and obtain an expression for V test over I test. That gives you, so all you're doing is, the idea is simple. If you want to find the resistance at a node, that's what you're interested in finding, right? RIB. This is a generic procedure that will come in handy in 109 when you take advanced analog electronics courses. Here is a general procedure. How do you get an analytical solution or even a numerical solution for a resistance at one particular node? Okay, what we do is to deactivate all the independent voltage sources, apply a test voltage, and look at the current. Okay, so if you consider all of this as a black box, okay, if you consider all of this as a black box, Okay.
So, like black box means just ignoring it.
Black box meaning that not just ignoring, you want to abstract the behavior of this. You you really are not bothered about what goes on inside this box. You just want to understand how it behaves on these external terminals. Okay, there is this terminal, right? So looking into this, okay, all you care about is looking into this box, how much resistance do you find? Okay, that's what I mean by black box. Do you see what I mean? It does not matter to me what is sitting inside here. I don't care about what is inside here as much as I care about what's its resistance, what's its terminal behavior is. So in that sense, I use the word a black box. Does that make sense at all?
Yes.
So at this terminal, what is its resistance? Okay, then in order to find the resistance at that terminal, what you'll do is you'll apply a test
Vx.
voltage. Correct. You'll apply a test voltage V test and look at how much test current is flowing. That will give you the resistance looking in. Okay, that's the generic procedure that we will follow. Okay, and it involves a whole lot of crappy algebraic manipulations. Okay, I'll show you some of them shortly. Okay, but that's the general procedure. Even when you're calculating IB, that's the exact same thing. Even when you're finding out RIC, that's the same thing. When you're calculating RIE, it's exactly the same. So let's apply this process here. Okay, RIB is the resistance that I'm interested in finding. That's the resistance at this node. Okay, so what I want to do is to apply a test voltage here. Okay, first thing I want to do is to deactivate any voltage sources, any independent voltage sources. But we don't do anything to the dependent sources. We leave them like this. This is a dependent source. We don't change it. Any independent voltage sources are short circuited. Any independent current sources are open circuited. Okay, then we apply a test voltage. Okay, we apply a test voltage V test. Okay, and I want to look at the I test. So let me start by doing that. And once I do that, the first thing I want to do is to write the KCL, the emitter. Okay, there are three nodes. So if you think about it, R Vx is an unknown, Ix is an unknown, okay, Ve is an unknown, and I naught is an unknown. Okay, there are a bunch of unknowns, and then we are going to use some of them. Okay, we are going to use tactfully in arriving at a solution that I want. Okay, let's start by writing KCL at this node. Okay, at the output node, KCL at the emitter node. Let's start by the emitter node, that guy. Okay, let's start KCL at this node. Okay, so let's identify the currents that are going in. Okay, there is and currents going out. There is one current that's going through this guy. Okay, if I call VE is the voltage dropped across this resistance, when I'm writing KCL at this node, right? So this is KCL at the emitter. So that's purple node here. So that branch is this guy. So that's the current. Okay, that's this current. The purple current flowing in here. Okay, that's this guy. See, the voltage dropped across the resistance VE over resistance IRE gives me that current. Okay, that's the current leaving this node. Okay, also think about a current through this node. Okay, there is a current. If you think about it, there is this current that's leaving this node. Okay, Let me see. Okay. So there's a current that is leaving through the resistance R naught. Okay, so that will be the voltage over here. Okay, that's the voltage over here, which is VE, minus the voltage over here, which is negative I naught RC over R naught. So all I'm doing is the voltage across these two terminals divided by that resistance. Okay, VC minus negative I naught RC over. So here is the current leaving in this branch over here. Okay, I'm writing KCL at different at this node, at an emitter node. Okay, and then if you don't trust me, you can see what is the voltage here. It is I naught times RC. Okay, that's the voltage at this node, right, which is the same as this node. Okay, because I'm considering the current flowing in the opposite direction, I pick up, okay, I pick up an additional negative sign. So this is supposed to be VE minus the voltage over here, okay, by R naught, okay. Now, those are two currents. What else? Okay, let's not forget this current over here. Okay, that's this current that is beta times IB. So this is beta times IB. And then there is another current here, blue current, IB current flowing here. Okay, so there is new strict COVID-19 measures in the US. Okay, so if I add them up, I have beta plus 1 times IB. So all I have done is to look at all the currents at the purple node here. Let me see if I can. At the purple node, there are 4 different branch currents. Okay, I added the currents leaving and the currents entering. Okay, now the current leaving is the purple current flowing down and the green current flowing up. Okay, similarly, now the currents coming in are these guys. Okay, the currents coming in are the beta IB plus 1 IB. So currents coming in equals to the currents going out. That's the KCL over here. Okay, that's the idea of KCL. Let's see if we can do the everybody with me so far?
Yes.
Okay. So let's do the KCL at the collector. Okay. So I'm going to erase this part. Okay, just so it doesn't get too crowded. Okay, I'm going to erase all of this. I want to do the KCL at the collector. Okay, let me pick this node, collector node. That's the node I'm interested in when I'm calculating the current. Okay, now the current leaving. What current is leaving? There is one current that is leaving over here, beta IB. Okay, there's one current that's leaving this node. Okay, what are the currents that are entering? There is one current I naught that is entering. Therefore, I have this current that is entering. Okay, plus there is another current. There is another current that is entering to this guy, through this guy. Okay, so that corresponds to voltage here. Okay, that corresponds to the VE minus the voltage here. Okay, the voltage here is voltage at that node collector is negative RC times I naught. Okay, so negative of negative RC times I naught over R naught gives me the current in the green branch. Okay, that's the current in the green branch. Okay, this voltage minus the voltage here. Okay, the two ends of the resistance divided by that resistance. Okay, so that gives me this. This is R naught times RC times negative I naught. Okay, so now this gives me the green branch current. Okay, so that's the idea. That gives me KCL at the collector. So this is equation 1. Okay, and here is an equation 2. That's my second equation. Okay, let me see if I can get a third equation. Okay, the third equation is KVL around this loop. Okay, the loop I'm going to choose is the input loop. Around that loop. Okay, so there is this loop, the input side. Okay, the input is on the base and the emitter, right? So I'm going to go through this, all of this loop. Okay, because both of these are ground, right? So I'm going to use that as a loop. Now, the idea of KVL is that the voltage dropped in each of these resistances should equal the voltage applied. Okay, the voltage dropped in each of these resistances will equal the voltage that is applied, and you can write it as Ix, or the test current Ix, times R pi, Ix times R pi, plus the voltage dropped across this VE. Okay, the voltage dropped across the RE resistance VE should equal the voltage applied Vx. Okay, the total voltage that is applied Vx should equal Ix times R pi plus the voltage dropped across this resistance. Okay, which is VE. So rearranging that, I have Ix equals to Vx minus VE over R pi. Okay, so that's the idea of the KVL around the input loop. Okay, the loop I'm using is this kind. Okay, around that loop, KVL loop. Okay, once I do that, I get the third equation here. Okay, I get the third equation. Now there are 4 unknowns and 3 equations. So there are a bunch of so I cannot find the value separately, but I still can find the ratio Vx over Ix. Okay, I can find that separately. Okay, so now it's just a matter of massaging these equations 1, 2, and 3 to express it in terms of Vx over Ix. Okay, if you remember, my argument to begin with was, if I think of all of this as a black box, okay, if I think of all of that as a black box, okay, resistance looking at this node, okay, at the input node, okay, is simply Vx over Ix. Okay, sure enough, using the equations here, 1, 2, 3, I should be able to calculate, should be able to derive an expression for Vx over Ix, which appears something like this. Okay, because we are engineers, we care about numbers. We also care about, we don't want to pay too much attention to unnecessary accuracy. We don't want we, we are always interested in finding smart, intelligent trade-offs. So if I can trade off accuracy for a little bit of intuition and ease of remembering, that's always welcome. Okay, so I'm going to approximate all of this. I'm going to approximate all of this to be r pi plus beta 1 plus 1 times re. The idea is that anything within this parentheses, okay, this guy is going to be close to 1. Okay, that's the idea. Okay, this is almost close to 1 is the understanding, because r naught is such a big number. R naught is such a big number. In comparison, these appear small. Okay, these appear small. Remember, I gave you the reason for why R naught is such a big number. Okay, I told you maybe in here, see, the slope of this guy is so small that it's almost close to 0. If you take the inverse slope of it, that is R naught. And because the slope is small, the inverse slope is extremely large. So by that argument, R naught is so large that these teeny tiny numbers don't make a whole lot of difference between the numerator and denominator. And I'm going to approximate them to be equal, the numerator and denominator. So I'm going to approximate all of that to be r pi plus beta plus 1 times re, because it provides us intuition. Okay, the intuition that we wanted to see was looking into the base, the resistance has r pi and an amplified reflected up version of re. Okay, remember I kept saying that over and over and over again. Okay, looking into the base, I find r pi and a reflected magnified version of re. That's the intuition I'm after. The rest of the stuff, they don't provide as much intuition to me, and they're not adding so much value in terms of accuracy. So I'm going to approximate them within reasonable limits to be close to 1. Okay? So that's the idea of, and that's the exact same process we use for solving the rest of the RC as well. When we are calculating RC, for example, we write KCL and KVL at different nodes. Okay, so we notice that the same current that is entering in I test is actually branching into 2 different branches and then eventually combining together. Okay, it's combining through through RE. So we use some observations, but still KCL at different nodes, and then calculate those expressions. Okay, so still applying the exact same Kirchhoff's laws. Okay.
Professor, like for the exam, do we need to just get to the final results we are getting?
For the exam, you just need to remember these results. Okay, you can go through this slide. Okay, like I said, you may want to get it tattooed or have it written on a page. Okay, write it on a page, have one formula sheet. Okay, if you remember these, okay, this is the final result. Okay, the final result, that's enough. Okay, but I just wanted to show you, in the interest of completeness, how we arrive at the final result. Okay, by applying KCL. In this class, you don't have to be 100% comfortable with writing these equations, but hopefully, if you practice this enough in your engineering 17, engineering 1, it shouldn't really be too intimidating. Okay. For now, it's okay if you want to remember the final result or write the final result down on a paper. That's fine with me. Okay. For your exam, you can use a cheat sheet. Okay. So that's the idea of BJT, single transistor amplifiers. So let's look at the exact same thing for MOSFETs as well. Okay, for MOSFETs, I'm probably not going to dive into the details as much as I did into the BJTs. I will only point out to you the final results. That way we preserve the intuition. Okay, so let's start with the summary again, like it is our usual habit. Okay, when we are looking at the MOSFETs summary, okay, when we look at the summary of MOSFETs, so this is something we looked at in the last class. The common source amplifier is a bread and butter gain stage. It provides good gain stage. It is bad for driving small load. The common gate amplifier is good gain stage, but bad for driving small load. The common drain amplifier, which is the source follower. Remember the common collector amplifier in BJT, which was the emitter follower. Okay, that emitter follower here is the source follower in MOSFETs. Okay, so now let's look at the common source amplifier and see if we can get some. Um, the MOSFETs are easy in the sense that when you're looking at the input resistance on the gate, okay, our input is ideally and reasonably close to infinite. For reasonable values, it's high. It's extremely high because the current going into the gate is really zero for an ideal MOSFET. Okay, there are situations where there may be some current, leakage current going into the MOSFET, but ideally speaking, the current going into the MOSFET gate is zero. Okay, similarly, let's look at the, or let's go back here. The shortcut approach. Let's look at the shortcut approach. Okay, so that's what I mentioned. Resistance looking into the gate is infinity. This is applicable at low frequencies. Resistance looking into the drain. Okay, resistance looking into the drain is, notice, RID. So that's this guy. RID is R naught, that is multiplied by 1 plus GM plus GMB plus GDS times RS. Okay, GDS is again 1 over R naught, right? So what you will do is the idea simply is because of the source degeneration, if it were not the case, if there was no source degeneration, and this you'll see this in the next class, maybe in 109, hopefully, if there was no source degeneration, your RID becomes simply R naught, because that will be the resistance looking into the drain is R naught. Okay, but because of source degeneration, what happens is the resistance R naught, okay, is multiplied by a really large number. Okay, I'll give you a crude approximation for all of this. RID, the resistance looking into the drain of a MOSFET with a source degeneration, is approximately, okay, R naught times GM RS. Okay, it's a very crude approximation. Okay, I'm going to ignore a whole bunch of terms. I'm going to ignore this one over here. I'm going to ignore this GMB over here. This is coming from the body effect. I'm going to ignore this GDS, which is 1 over R naught. R naught is large enough that I can ignore GDS. Okay, so a crude approximation is RID is R naught multiplied by GM times RS. Okay, so in other words, just by adding a resistance in the source here, the output resistance here is going to be multiplied by R naught, is going to be multiplied by GM RS. Okay, so that's the intuition that you get. R input looking into the source. So that's our input looking into the, that's RIP. Let me color code them carefully. Looking into the drain here is this guy. Okay, looking into the source, if you're looking into the source, okay, if you're looking into the source, you'll find 1 plus GM plus GMB. This is an interesting result, okay, times 1 plus RD by R naught. Okay, the resistance in the drain appears to be divided by R naught. Okay, so, and the resistance in the source by the resistance in the drain. Okay, 1 plus RD by R naught. Okay, so 1 plus GM, 1 plus GMB plus 1 plus GDS. Okay, and then you can find out the trans conductance as well. So here's the shortcut approach. Once you know the three resistances on the gate, the drain, and the source, you should be able to calculate using the three currents. Okay, if you want to calculate the gain of a common source amplifier, the gain of common source amplifier is the output over V input. V output is nothing but I output into R output. So using Ohm's law and the resistances that we just used, that we just expressed in terms of algebraic expressions, we should be able to calculate the gain, overall gain. Okay, common source amplifier has GMRD by 1 plus GM plus GMB plus GDS times RS. Okay, what do you think happens? Is this, how can I ask, what do you think happens if RS becomes 0? If I short circuit that, then all of this term is going to go to 0. So I'm going to be left with negative GM RD by 1, or negative GM RD. That's the maximum gain that you can get for a resistance RD. Okay, the intrinsic gain of a MOSFET is negative GM R naught. Okay, R naught in parallel with RD can be approximated as negative GM RD. Okay, because R naught is so large, a large value in parallel with a small value gives you a small value. This is RD. Okay, so that's the approximation. Negative GM R naught in parallel with RD. So this is what is happening. RD in parallel with a really large number, a really large quantity. Okay, so it's going to be approximated as RD. A large resistance in parallel with a small resistance is a small resistance. That's the approximation here. A large resistance in parallel with a small resistance is the small resistance. Okay, that's the idea. So the gain can be expressed as negative GMRD by 1 plus GM plus GMB plus GDS times RS. Okay, so that's the common source amplifier bread and butter gain stage. Okay, bread and butter gain stage. Similarly, you can look at the common gate amplifier, which will give you a gain that looks like this: GM plus GMB plus GDS RD by 1 plus GM plus GMB plus GDS times RS plus RD by R naught. Okay, based on the fact that the input and the output resistances are like that. And then there is the common drain amplifier. This is similar to the common collector or emitter follower amplifier. Okay, so that's the idea. Now the gain of this guy is almost close to 1, but definitely less than 1. Okay, it's close to 1, definitely less than 1. Okay. So the dominating term here is GM. GM by GM. GMB is a small quantity. GDS is a small quantity. GS 1 over RS is a small quantity as well. Okay. All right. Let's see. So that's the idea of single transistor amplifiers. So here is a quick comparison. Let me see if there is an analysis showing the calculation of RS looking into the source, RID looking into the drain, so on and so forth. So here is again the calculation of RID. Okay, when you're all you have to do is when you're the familiar I test, V test voltage, test current method. When I'm interested in calculating the RID over there, when I'm interested in calculating this guy, I apply a test voltage, I apply a test current, and divide V test by I test, or Vx by Ix. And then I write, make some observations, the exact same things as in calculation of I or RC, RIC. Ix, the current that is flowing in here, is going to split into 3 branches, okay? And it's going to add up in the RS resistance down below, okay? So the first observation that we do is this Vs, the voltage dropped across this guy, is really RS, this resistance, times the current flowing through this. Well, the current flowing through this can only be coming from these 3 branches, okay, which are all emanating from this Ix. So this ought to be Ix, okay. So that's the observation, the first observation I make. And then based on that, I write this equation, Vs is Ix plus Rs. Then I can sum the currents here, VGS, okay, VGS equals to VBS equals to Ix times Rs, negative Ix times Rs, okay? And then Vx is Vs plus I1 times R naught, okay? So if you think about it, there is a current I1 flowing through this resistance. This guy, okay, this voltage is the voltage dropped across this resistance and the voltage dropped across that resistance. Both of these should add up to the voltage that I apply. Okay, the KVL idea. Okay, this is the KVL idea, and then the above one is the KCL idea. Okay. Okay, so once we do that, we should be able to see the value for, we should be able to see the expression for these. So let's quickly summarize what we have so far. BJT, common emitter amplifier, and MOSFET common source amplifiers are very similar. They can have large negative inverting gains, okay? They provide high input resistance and high output resistance, okay? Similarly, the common base and common gate amplifiers are similar. They can provide large positive gains, okay, with low input resistance and high output resistance. And by the same token, okay, the common collector and common drain amplifiers are similar. They provide almost no gain, close to 1, with high input resistance and low output resistance. Okay, so whenever you have anything going into the base and the input is on the base, okay, or the gate, then your input resistance is extremely high. Okay, and that's the idea. Okay, and I mentioned this in the last class. BJTs provide higher voltage gain than um, field effect transistors because the GM R naught is much smaller, is smaller than um, the GM of MOSFETs is smaller than the beta of the BJTs. Okay, BJTs provide greater GM, it is provide higher resistances than BJTs. Okay, so here is the quick summary. Amplifiers are usually modeled as unilateral two-port networks. Thevenin's voltage equivalents and Norton's currents equivalents are used. Okay, Ri and R0 are used to determine the signal loss. Okay, the amplifier is determined by where the input is applied and the output is measured. So the resistance looking into the terminals are the same for BJTs and MOSFET op-amps. Okay, we use the shortcut approach. We simply look at the resistances, multiply them by the currents to get voltage gain, and divide V output over V input to get the voltage gain. Okay, and then BJTs and MOSFET single transistor amplifiers have a lot in common. Okay, so that concludes all the chapters that I want to talk about. I really want, and let me do this. Let me clean this up, just so when you go back and look at this study material, you're not, it doesn't look crappy. Okay, so to the extent possible, I'm going to clean this up. Okay. Okay, now this concludes all the topics I wanted to discuss in this chapter. And as a matter of fact, I really want to congratulate you for sticking with me through this semester. It has been quite a ride, extremely busy summer semester. Okay, I want to congratulate you. It's a Herculean task to be able to keep up with the pace at which the summer semester goes. Okay, it has been a pleasure interacting with you. Obviously, we value your feedback. I threw in an extra credit opportunity to encourage you to provide your feedback. If you do the end of the semester course evaluation, okay, you can feel free to mention, you can feel free to provide your comments. You don't need to show me those comments. All I need to know is one confirmation screen that you finished it. If you upload it to the extra credit page on Moodle, that will give you a small trickle of extra credit points that add to your final percentage. Okay, so it may not be a whole lot, maybe 0.5 or less than a percentage, but that's more. Less is more when I'm adding to the final percentage, because if you're on the borderline between A and A plus, this would be this could be enough to push you over that line and boost you to the next grade up. Okay, so a small extra credit, a small one that adds to your final total. So less is more. Okay. All right. So I encourage you to finish that. There is a deadline of 7/1/2020, and notice that it is alongside the exams. Okay. So how about we take a break tomorrow? Since we finished all the material, we finished. Let me see. Let me do this. Let me start.